All right. So we are picking up on inscribed angles. So we are on 10-3, right? Because you had already done everything up until then. In the notes packet I'm talking about. Right? You did all the things before. Okay, perfect. All right. So we mentioned inscribed angles yesterday. Here's a good picture of them right over here. So you've got an angle whose vertex is on the circle's edge. That's what an inscribed angle is. Okay, so that is what we refer to as an inscribed angle. And then if you take any inscribed angle and just kind of keep the angle going, you'll see that it sort of cuts off a chunk of the circle. That piece of the circle's edge there, we call that the intercepted arc. So what I just highlighted right here in orange. Okay, so that would be the intercepted arc of that inscribed angle. All right, let's see. The arc that lies in the interior of an inscribed angle and has endpoints on the angle is called the intercepted arc of the angle. Okay, and then this next theorem, you actually proved this yesterday. We talked about this in the homework problem. What did we find out? Imagine you don't see it right there. What is true about the angle of the measure of this angle in relation to its intercepted arc? Its value was, remember? Half. Yeah, so if you know that the arc is, say, 100 degrees, that means the angle has to be 50 degrees. And you can go the other way. If you know that the angle is 50 degrees, you know that the arc's got to be 100. Okay, so, and that's different than, remember, take a look at this image down here. Here you have a central angle, ACB. And then you have an inscribed angle, ADB. So let's say I told you from A to B was, I don't know, let's say that's 120 degrees. What's the measure of angle ACB? It's 120 because that's a central angle. So when you have the vertex on the center, that's 1 for 1. Whatever that is, that's exactly what that is, 120. Those are going to be the same. Same Z's. Central angles and the arc, same. But the inscribed angle, so ADB is now going to be, that's the one that's 60, because that's the inscribed. Okay, so that's the big difference. So it's important to know the difference between an inscribed angle and a central angle. Okay, and you've got the formula right here. Remember those weird little A's just in the arc. So the measure of that inscribed angle is going to be half of its intercepted arc. Does that make sense so far? You remember talking about that yesterday? We had that problem where you like investigated and you found out that that would always be true. All right, so let's flip. Pretend you don't see that for a second. Let me cover it. Just look at this picture. So I have two angles in here. I have angle ACB and angle ADB. See how their intercepted arc for both of them is arc AB? Do you see that? Both of those inscribed angles have arc AB as its intercepted arc. You with me so far? See how they both share that? So what does that mean about angle C and angle D? What must be true? They have to be equal. They're both half of the same arc. So if I told you arc AB was 80, they'd both be 40, wouldn't they? Right? Doesn't that make sense? So if two inscribed angles, if they share the same intercepted arc, they have to be equal to each other. That's all this theorem is saying. So angle C must be congruent to angle D.
That also goes for angle A and B.
Correct. Angles A and B would have to be the same too because they share intercepted arc CD. Ooh, I didn't even pick up on that. So interesting. Gosh, I love circles. All right, take a minute or two and try 1 through 6 here. Just 1 through 6, don't go on past that. So remember all these, those are just arcs, okay? So wherever you see that little A or some of them are little O's. All right, try these 6, we'll see how you do. One through 6, yep. I'll give you another minute maybe. Okay, ready? I'm not calling you at random. I feel like I haven't done that in forever. Here we are. Okay, number 1, what did you get? Julia? 76, you said? I agree, 76 for that one. Number 2. Jack is not here. Patrick, number 2. I agree. 3, Taylor. You got what? Oh. Want some help? Well, remember what you've got this arc here, that's 160. So the inscribed angle, what did we just say it was? It's not going to be equal to 160, it's half. 80. Did you have 160?
No, I'm not.
Okay. Does it make sense now?
Yes.
Okay. 4. Oh, the K is not here. Oh, honestly, I literally picked yours next. How about that? That's crazy. You are right. 80. Which means, what conclusion could you make about line segment BC? I know it's not drawn, but what must line segment BC be? True, but you be more specific. It's got to be a, Isabella, diameter. It's got to be a diameter, right? If this whole thing is 180, that's half a circle. So BC would have to be a diameter. How interesting. 5, Liam. Do you want some help? It is 12. If you have the arc, you just take half. Deanna, 6, what'd you get? 16, that's it. Okay, so we're all right there. You have the arc, you take half. If you have the angle, you double it, right? You got to be able to just remember that the arc is always bigger. Oh, why did I just mix them all together? I wasn't done. Oh, well, you might be back in the mix. Whoopsie. All right, let's look at example number 2. What are they asking us to do here? So here they want us to find the measure of the arc or the angle. All right, so when you see something drawn like this, right, you know that M is the center. How do I know? Because they're calling it circle M. And if you would, even if they didn't call it circle M, if it's drawn like this and there's a dot that looks reasonably in the middle, you can assume that that's the center. Okay. So what do you know about segment PN? It's a diameter. So what does that tell you about arc NOP? Let's say, what's the measure of arc NOP? It is, so its measure would be 180, right? So you could find arc NO if you needed to. You can do the same thing on this side and find arc QP. I think that's a Q. It's a little hard to tell. So go ahead, try these 7 to 14. I'll give you another minute or two or a couple. Remember, anywhere you see that little A or little O, it's just an arc. And be careful, number 7 is QMP. So they're looking for QMP. What is that? It's just the arc symbol. It's just a, I assume they had a, whatever software they were using would make it arc for them. The little A and the little O just are the arc symbol. Bless you. Okay, we got some? Yeah, hopefully. All right, so before we get into it, let's go ahead and just find some of the pieces that we're missing. What would arc QP have to be? Arc QP right here. Patrick? Yes, 60. Because remember, here's the diameter. So that whole thing is 180. I had 120, that's got to be 60. I'm going to do the same thing over here. And O, that arc would have to be, shut it out. 110, yes. Nice loud shouts. Good, okay. 110, right? And this is a diameter, right? So that's got to be 180. Yeah. So the first one they're asking for angle QMP. So you have to draw in that. So QMP, isn't that a central angle? So central angles are just going to be the same as their arc. So if the arc is 60, that angle is 60. So number 7 should just be 60. Does that make sense? So when the vertex is on the center of the circle, you don't do anything. Just whatever the arc is, that's what the angle is. By the way, if you ever forget that, it's very easy to kind of see it. If you're looking at, you guys know that 1/4 of a circle is 90, right? And you can see it so clearly here. You know all the way around is 360, so you know that this is 90, and you know that this is 90. So you can see that one-to-one correlation there. So if you're ever forgetting, like, shoot, was the inscribed angle half or is the central angle half? I don't remember. Just go back to a basic circle like this, where you're like, oh, yeah, they're definitely the same. And then if you draw yourself in an inscribed angle, you can clearly see that it's much smaller. So you're like, oh, yeah, that's half. So that's got to be 45 in this case. All right. So any hoosers, back to the one in question. Number 8, angle NMO. So again, you want to draw this radius here, and you're looking for this angle right now. NMO. What did you say that was, Cole with a C? You are correct, 110. Because that's a central angle. So whatever the arc is, that's exactly what the angle is. Okay, number 9, angle PNO. Now we have an inscribed angle. So, oh my gosh, I keep picking the people that are not here. Elizabeth.
35.
It is 35 because it's going to be half of its arc, which is 70. Those are the ones you got to take half. Does that make sense? Everybody's all right? Okay, 10. Not here. Ava, what'd you get on 10? You are correct. 30 degrees for that one. QNP. So that is another inscribed. So if you know that's 60, that one's got to be 30 up there. Now on number 11, we're switching to the arcs. So Bryce, you have 11 arc QO. Oh, you're close. 130, I think. Right? 70 and the 60 together gets us to that 130. And how about 12? Arc NOP. Leanna, what'd you get there? Say it again. Yep. 180 is correct. Okay, and 13 is arc PQ. We already have that at 60. Couldn't do some of these other ones without that. And 14, OQN. Isabella, what'd you get for OQN? I have 250, but did I add wrong? What's 180 and 70? I think it's 250, right? Yeah, 250. Okay, so how do we feel about that? Inscribed angles are okay-ish. You just got to remember that it's half of that arc. Yeah or no? Yeah. Okay, okay. So let's see what they're talking about next. If all of the vertices of a polygon lie on a circle, the polygon is blank in the circle. So this is a term that we use when you draw a shape inside of a circle and all of the vertices are on the circle's edge. If that is true, then we say that that polygon is inscribed in the circle. Inscribed, you drew it on the inside. But then we can also talk about how the circle is drawn around the shape, and we use the term circumscribed. Okay, they mean basically the same thing. So I could say to you, hey, draw me a pentagon inscribed in a circle. Or I could say, hey, draw me a circle circumscribed about a pentagon. We're saying the same exact thing. You would draw this very same drawing. Okay, they mean the same things. Now, if I asked you to, let's try it this way. Try and draw it. Try and draw what I said. Try and draw a circle inscribed inside of a triangle. What would that look like if you drew a circle inscribed in a triangle? Circumscribed. Okay, so when what did I say? I said, draw a circle inscribed in a triangle. You should have drawn something like this, a triangle, and then your circle would be on the inside. Whatever is being inscribed is on the inside. Circle inscribed goes inside whatever the shape is. Okay, so there's the difference between those two. Depending on the wording, you could describe it different ways. We usually use inscribed though, so that's the one you're going to see more frequently. All right, now theorem 1010 here. This is so cool. So let's read it and then I'll break it down for you and we'll see what the heck is going on. Let me zoom out a little bit so we can get the picture too. All right, here we go. So let's read what it says. If a right triangle is inscribed in a circle, so we have a picture right here. We have a triangle inscribed inside the circle, all right, a right triangle. Then the hypotenuse is a diameter of the circle. Okay, before we go on, hold up. So you mean to tell me that if this is going to be a right triangle, that this has to be a diameter? Do you think that's always true? Draw yourself, find a piece of paper somewhere, draw yourself a circle, and I want you to inscribe in that circle a right triangle. Make it really look like a right triangle. And see if your hypotenuse looks like it's the diameter. Try all different types of right triangles. So I like to start when I'm doing this, try and start with a 90-degree angle. So draw yourself what really looks like a 90-degree angle. And then if I finish that off, oh, wow, yeah, so that really does look like a diameter. I want to try and get it so that it's not. Is there any way that I could, maybe there's some configuration of right triangle. Maybe I could do like a really short and then, check it out. Well, that one I didn't do very well. Ah. I used to have like a circle stencil somewhere. Draw yourself a right angle in that triangle. And when you draw that hypotenuse, the claim is that that hypotenuse is always going to be a diameter. But wait, doesn't it actually make sense? If this is going to be 90 degrees, isn't this an inscribed angle? Right? Isn't that an inscribed angle right there where I put that 90-degree angle mark? Right, you with me? So what must the measure of this arc be? If that's 90, what's this arc have to be? Gotta be 180. So you're guaranteed that that will always be a diameter. That is so crazy to me. And think about it. You could take, if I took just this 90-degree angle and I moved it over here, let's say. Doesn't matter. Put it over here. Doesn't matter. You're always going to have the diameter as your hypotenuse. Fascinating. I know, it's crazy. There's so much to these circles. All right, cool. Now let's read what it says. Conversely, if one side of an inscribed triangle is the diameter, then you know that the triangle must be a right triangle, right? We can go the other way. So if I'm starting off with a circle where I know, like here in this depiction, I know the AC is a diameter because it goes through the center. That means I know the angle B has to be 90, right? Because I know that this whole arc has to be 180. And that's got to be half. Okay, so I can go either way. If I'm going to inscribe a right triangle in a circle, the hypotenuse must be the diameter. Or if I have a triangle drawn so that one of its sides is the diameter and all vertices are on the circle's edge, it must be a right triangle. That's so cool. All right, let's look at the next one. It says, a quadrilateral can be inscribed in a circle if and only if its opposite angles are supplementary. Okay, if you take any old quadrilateral, you may not be able to inscribe the circle, or I'm sorry, you may not be able to inscribe it in a circle. Take a rhombus, for example. If I take certain types of rhombi, like that, there's no way that I could have a circle that hits all of these vertices, right? It'd be like some weird oval shape. You with me? So this cannot, that particular shape would not be inscribed in that circle. So the claim is, if I can inscribe the shape inside of a circle, the opposite angles must be supplementary to each other. And that kind of makes sense. So let's look. I'll just draw some random four-sided figure inside this circle. So I'll just pick 4 random dots. 1, 2, I'll put a 3 here and a 4 here. So this is just some random 4-sided figure, right? So the claim is that this is only possible if these angles add up to be 180, as well as these add to be 180. Can you see why? Why would that have to be true? Let me throw some letters on here. Let's just talk about angle B for a second, right? Wouldn't angle B, that's an inscribed angle, right? Right, you with me? So wouldn't it be equal to half of its arc, right? Which would be ADC. So this is going to be half the measure of arc ADC. Whatever it is, right? I don't know what it is, but I know it's half of it. You with me so far? Let's talk about the angle opposite of angle B. Angle D. Wouldn't angle D have to be half of its arc? And what's its arc? Its arc would go from A past B all the way to C. So U would be half the measure of arc ABC. Look at those two arcs. Look at them. Together, don't they make a full circle? Do you see that? Aren't I going around the whole thing completely? If I'm looking at the two opposite angles, I'm covering both of their intercepted arcs create my entire circle. And they're each equal to half. Right? So if the whole thing is 360 and they're both half of that, wouldn't it make sense that they would both have to add up to be 180, half the full circle? Because together, right, their arcs are the full circle. And they are half of their arcs. So anyway, the important thing to remember is that if you have opposite angles, right? If your shape is inscribed in a circle and you have opposite angles, they must be supplementary. So D and F have to add to be 180. E and G have to add to be 180. Isn't that neat? You can't inscribe a shape inside of a circle unless its opposite angles add to be 360 if we're talking quadrilaterals. So let's look at the examples down here. 15 and 16, they want to know, hey, could you draw a circle around these? A perfect circle, right? We're not talking some weird wobbly garbage. So how would I tell?
All the points have to be on the outside of the circle.
Mm-hmm. You say no? Well, I can know for sure by doing the math. We just said that the opposite angles have to be supplementary. So let's see, 130 and 70, are those supplementary? No, so I don't even have to find this missing angle in this one because I already know the answer is a no. Right, because 130 plus 70 is 200. That's not supplementary, so this is a no. How about 60? 130 and 50. Okay, that's 180. So we have one side that's working in our favor. Do you know for a fact that these other two are going to add up to be 180? Leanna, why do you say yes? Exactly. It's still a quadrilateral, right? No matter what's going on. It's got to add to be 360 altogether. I already have two that are adding up to be 180. So these other ones have to add to be 180. So I have one set that's supplementary and I'm going to have another. Even I don't even have to take the time to find what those are. You can. You don't even need them. They have to add up to be 180. So this one's a yes. Isn't that neat? Jump 17 for 1 second and just look at 18. Can you write an equation that would solve you for x there? Go for it. Try it. Okay, who can tell me what the equation is? Not the answer, but what's the equation that you would write for 18? Sam, go ahead.
3x minus 8 plus 5x plus 2.
Correct. We know it has to equal 180 because they are opposite angles of an inscribed quadrilateral. And we just learned that, hey, if you can inscribe a quadrilateral in a circle, which clearly they did, the opposite angles must be supplementary. So there's your equation, and now you just got to solve. This doesn't work nicely, does it, or does it? What's 186 divided by 8? What'd you get? Uh, 23.25. It's not so bad. Right? Is that what you guys got? 23.25? Yeah. Does that make sense? All right, jump back to 17. What are you gonna do with this thing? Eva? Exactly. These two are equal to each other. These are inscribed angles of the same arc. So even though I don't know what this arc is, it doesn't matter. They'd have to be equal to each other. So 3x should equal 2x plus 13. And then that one's nice and easy to solve. You just get 13 there. Does this make sense? Is everybody okay? Are you with me? Are you loving circles? Are you seeing how cool they are? Oh my God, I went just at the tip of the iceberg, people. Oh, and that's it. I mean, we could keep going, but. Yeah. All right, so let me just double check the assignment that I have written down, make sure I didn't totally goof. All right, 354. All right, 109. No, those are good. And then 19. Okay, this looks good. Let me go ahead and write this down for you. All righty. Okay, so let's give this a try. Please ask me questions if you are stuck. And we'll go from there. Oh, Jesus, my hair tangled in my rubber band.